Hey guys, welcome to the video where today we'll be talking about the energy levels in electrons. If you guys have not already, make sure you guys check out my other videos where I make a lot of the topics your professors talk about that are very hard into very simplified videos. They help out a lot, so go ahead and check those out. And then you guys can knock your crazy professors on top of their head and come watch some of these videos. So without further ado, let's get right into it. So energy levels in electrons. What is energy? So energy is the capacity to cause change. An example of this is by doing work. In previous videos, we talked about many types of different reactions where maybe you're trying to catabolize something, meaning you have these very small molecules and you're trying to make it into something much bigger, right? These large macromolecules. Well, we can't do this at all unless we have energy, right? When you are tired, fatigued, you haven't eaten anything, there's no glucose, for example, right? There's no glucose. Glucose is a form of energy that we use, to go ahead and cause these reactions in our body to happen. Everything is run by energy. But for today's video, we're going to just be talking about two different types of energy, right? And those types of energy is either potential or kinetic energy. Now for potential energy is the energy that matter possesses because of its location, right? And just stick that definition into your head. We will go into a more in-depth example, so this will all make sense. And then if we move over to kinetic, we can see that it is the energy matter possesses by being in motion. And I have this cool little Sonic character here, so this is a good way for you guys to kind of remember. Potential energy is because of its location, and then kinetic is because of motion, and we have Sonic here again. So now if we go over into the next slide, we can see an example here, right? So our example is this dam, or where this water is up top, this water is in the bottom, and it flows down, right, into this reservoir, right? Oh, I forgot how to spell reservoir, but whatever. At least I'm honest with you guys. So again, we have water that's up top here, and this is where the potential energy will be at its greatest. And then as it goes down, you can see here it says kinetic energy. Now that water is in motion, right? Again, motion. And now we have the water down here, and this will be a lower potential energy. Now, why is this? So at the bottom, if you guys see right here, I wrote that the energy of the water at the top of the hill has more potential energy. The water at the lower part has less potential energy. Why? So I have a little hint that I wrote right up here. It says, science is lazy, precise, and smart, ... sometimes, which is true. So again, think. If you look at the previous videos that I talked about with energy and things of that nature, why would this happen, right? So let's go ahead and take a peek. Actually, I'll give you guys 2 seconds. 1, 2, and there we go. Here's the answer. The answer is matter has a natural tendency to move to the lowest possible state of potential energy. To restore the potential energy of the reservoir, work must be done to elevate the water against gravity. So let me read that again. Matter has a natural tendency to move to the lowest possible state of potential energy. To restore the potential energy of the reservoir, work must be done to elevate the water against gravity. So now if we go back to our little diagram here, maybe I can clear this up. Let's see. I'll just kind of clear some of this up, right? Now, if we look at it, let me pull out my pen. If we look at it here, we have the potential energy of water. It's very high potential energy, right? It's going against gravity. It likes to be in a lower state of energy. We always talk about energy where it wants to be in the lowest state, right? Which would be to fall down. It would be more favored for it to fall down than for that water to move back up, because if the water were to move back up, it would be going against gravity, and it requires energy or work for that water to be pulled right back up to this higher position. again, in energetics, it's lazy, or at least I like to say it thinks, why am I going to put in so much work to go back up when it would be more favorable for this water to fall down? All right. So again, this is why the potential energy is much greater at the top than it is for the bottom. So now if we go into our next slide, we're going to get a little bit more scientific. Now we have the examples out of the way. Now you can really think about atoms and the actual electrons, right? So electrons of an atom have potential energy because of how they're arranged in relation to the nucleus, right? So again, if we go back to potential energy, if we go back to potential energy, we know that it's the energy matter possesses because of its location, right? So if we look at an electron, its energy is based on its location, right? So if we skip over to this diagram we have here, and if we look to our right, where we have this orange looking color represents the nucleus that's in the middle, and then this purple one represents the electrons, right? So again, if we go to the image, we have the nucleus right here where I wrote a 1 in, and then we have 1, 2, 3, and 3 different electrons. Could you guys tell me which electron may possibly have the most potential energy? Correct. The one that will have the highest potential energy would be this one here, right? Remember, because it's based on location. So I kind of jumped ahead a bit, but this electron will have the highest potential energy. Why? Because these negatively charged electrons are attracted to the positive nucleus. So it takes work to move a given electron farther away from the nucleus. So let me kind of backtrack here and kind of give you guys an idea of what I'm talking about. So we have 3 electrons. We have one that's way, way far out, and we have one that's real close to the nucleus. It will take work for this electron to be moved closer to that nucleus, right? As to this one, it's already so close to the nucleus, it's low energy. So the further away it is from the nucleus, the further away that electron is from the nucleus, the more potential energy it has. Again, potential energy, think of its location. The electron that's closer to the nucleus will have a lower potential energy, right? And this kind of, if we go even deeper, this is why science is so interesting. So if that electron has more potential energy, we know that high energy electrons have the ability to more likely go through reactions. And this is, again, if you looked at my previous video talking about isotopes, radioactive decay, and how most reactions occur, we want to keep in mind that the outer electrons are the ones that are responsible for a lot of these reactions to occur, more specifically the valence electrons. But that's me skipping ahead a bit, but I always like to foreshadow and kind of excite you guys, right? And also another interesting thing I want to throw in here is when we talk about potential energy, and this is kind of off topic, but kind of something cool to kind of think about, and that's something you guys can probably gauge for yourself, do a little research. So when you have potential energy and you're going against gravity, like in this image, right? This water is not going to go back up because it's fighting against gravity. Gravity wins in this graphic where we have water and it goes down because of gravity as a force, right? Well, how about space? There's no gravity in space. So is there potential energy in space? That's something I'll let you guys figure out, all right? So now, if we continue on about energy levels, we can say that energy levels are correlated with average distance from the nucleus, right? Which I've already talked about, where we have the nucleus here, and we might have an electron here, and an electron right here. Again, this electron would have the higher potential energy. This one would have the lower potential energy, and this arrow is just a shorthand for lower, and then this upper one for higher. So the one closer to the nucleus will have the lower potential energy. And notice how I'm kind of reiterating a lot of these, because this is how I learn, and I think it's a great way. If you guys keep hearing it again and again and again, you guys will kind of grasp it better, where you constantly hear this guy Dre keep saying potential energy, further away, higher potential energy. Oh my god, I'm so sick of this, but that's the best way to learn, right? So if we go into what we call the shells, right? So this is very important. Here we have the nucleus, and then we have the first energy level, right? This first energy level. So we have three of them: the first, the second, and the third. In the first energy level, it can hold a maximum of 2 electrons in one orbital. For the second energy level, it can hold a maximum of 8 electrons over 4 different orbitals. Third level can hold a maximum of 18 distributed over 9 different orbitals. So what does this mean? We're going to get into this, okay? If we skip over to our right, we can see we have a hydrogen atom, and this is in the first energy level, or the first shell. If we look over at sodium, where I'm highlighting in red would be the first shell, and then where I'm highlighting in orange would be the second shell, and where I'm highlighting in blue would be the third shell. Okay, and then the same thing for aluminum. We have a first shell, second shell, and third shell. Okay, and I know you guys are probably tired of it, but could you guys tell me which electrons would probably, or which electron would have the most potential energy in sodium? All right, yep, right there. That one would have the higher potential energy, since it's further away from the nucleus. Okay, and that's just kind of me, you know, kind of trying to throw you guys off, try to see what's up, you know. Now, if we go even deeper, if we look at aluminum, which has the highest potential energy? Well, you can say, Dre, there's 1, 2, 3 of them that's far away from the nucleus, right? Which has the highest potential energy? Well, we know the one that's in the furthest shell, which is here, would have the highest potential energy, but which of those 3 have the higher potential energy? And the answer is, I don't know. And if you guys can tell me, that would be very nice. A lot of electrons, we don't necessarily know the exact position of them. We just know that they are in an electron cloud. And for the most part, we know that atoms are mostly empty space, but I want to be very careful when I say mostly empty space, because many would argue that it is not mostly empty space. It's just that the electrons are much smaller in their density compared to the nucleus. But these are all things that, you know, we try to figure out as scientists. We don't know exactly the location of the electron. We just know it's in the electron cloud, and that these electrons are further away from the nucleus. But where exactly, we don't know, right? Maybe one day we'll figure out. So now if we look at our next slide, let's look at these shells, right? So let's see. We have shell 1, 2, 3, and 4. And again, shell 1 can hold a maximum of 2. Shell 1 can hold a max of 2. Shell 2 can hold a max of 8. Shell 3, 18. And then shell 4, 18 plus, right? So let me see if I could blow up one of these. Let's see. Boom. Let's go to carbon, right? So carbon has 2 shells, where in the first shell it holds 2, because remember, in shell 1 we can hold a maximum of 2, right? And then in the second shell it has 1, 2, 3, 4, right? It has 4 electrons. And if we go back, shell 2 max 8, right? But why is there not 8 there? Because carbon only has 6 electrons, right? So it already filled up the, if I get my eraser here, it's already filled up its first 2, right? So now we just have 4 left over, right? 1, 2, 3, 4, and that's it, 6 electrons. Now let's go over to something like fluorine, right? Oh, that one popped up big. So in the first shell we can hold 2, right? And that's exactly what we did. And it has 9 electrons, right? So 9, okay, let me see if I can, okay, so 9 minus 2, right? 9 minus 2, we have 7 electrons left that we need to fill. And that second shell can only hold 8, right? But we're still in the clear because we only need 7. So we have 1, 2, 3, 4, 5, 6, 7. All right? And I hope the pen isn't like bleeding or too much, but okay, I can try that. I think that'll work. Because I don't know, this pen was just like real big. Like it's bleeding or something, right? It's a digital pen. But yes, if we look at one more, let's take phosphorus, right? So phosphorus has 3 shells, right? So let's see, the first shell we filled 2, and the first shell can only hold 2 electrons. The second shell can hold 8 electrons, right? 2, 4, 6, 8. So how many do we have so far? We have 2 from the first shell, right? We have 8 from the second shell. So now we have 10. And phosphorus has 15 electrons. So we're missing out on 5 more electrons. So where are those other 5, right? Those other 5 would be right here. So we have 2 here. That's 2, 3, 4, and 5, right? In the third shell. And the third shell can hold how much? The third shell can hold a maximum of 18, which is a lot. So that kind of fills up for phosphorus, right? And now if we look at another example and we look at something like neon, these are considered our noble gases, our inert gases. They are unreactive. They fill their outer shell, right? If we look at the rest of these electrons, they do not fill their outer shell. They can still hold more electrons just based on the maximums that we see right up here, right? Now, if we look at neon in particular, neon has 10 electrons. So in the first shell, the max is 2, right? And it's filled. The second shell, the max is 8, which we have 2, 4, 6, and 8, right? It filled up its shell. It's completely filled. Every other atom wants to be like these cool guys, these noble gases, right? Because they're so cool. They filled up their shell and their outer shell. It's filled up, right? And that's exactly why these are the inert gases, and they are unreactive. They don't have to be unreactive because their outer shell is completely filled, right? So these are the cool guys. That's neon, argon, and helium, which argon they use in a lot of labs as a carrier gas for gas chromatography. Pretty cool, right? You learn something new every day. So I hope you guys kind of got that. Ask any questions down below. Feel free. And then we go over to our next slide, and now we're going to get into orbitals and electron configuration, right? So we always talked about the first shell, we talked about the second shell, and so on and so forth. Now there's something called orbitals, right? And it's kind of like this 3D schematic that we have to represent the electron cloud, or electrons that are around the nucleus, right? So an example we're going to use is neon, right? Which I already drew out. And neon has how many? 10 electrons, right? So if we see in the first shell, we have 2, right? Because it can only hold a maximum of 2. The second shell, 2, 4, 6, 8. The second shell can hold a maximum of how much? 8, if we see right here, right? It can hold a maximum of 8. And neon has this fulfilled in its outer shell. But how would we write the electron configuration, right? Which I already pre-did right here, right? So it would be 1s2, 2s2, and 2p6, right? Now, where am I getting this from? Now, when your professors give that crazy exam, this is something that I highly recommend that you guys try to memorize. And it's this small chart that you guys can write out. So it's 1s, 2s, 3s, 4s, 5s, 6s. Bear with me, guys. I know this is kind of crazy. 2p, 3p, 4p, 5p, 6p, 7p, let's see, 3d, 4d, 5d, 6d, 4f, and 5f. So this is something that can kind of easily be memorized. Just think 1 through 7, skip here, 2 through 7, skip here, 3 through 6, skip here, and then 4 to 5, right? So let's see how we're going to do this. So we know that neon has 10 electrons, right? So, and we know that the first shell can only hold 2, right? S can only hold 2. So let's write, S can only hold 2. The P, which is the p orbital, can only hold 6, right? So what we would do is we would cross this out, because remember, we're trying to get to 10, 1s2. And this number up here will add up to the number of electrons that atom has, right? So let's go back to my red. So 1s2, we could cross that out. And let me use a different color for this. Then we're going to do 2s, cross out 2s. And we know that S can hold a maximum of 2. So this would be 2s2, right? And now we go to the next one. We can cross out 2p. And we know that the p orbital holds a maximum of 6. So this would be 2p6, right? And now if we add up those exponents, I call them, 2 plus 2 plus 6 equals 10, right? And that's exactly how many electrons is in neon, right? So this chart is very important and something you want to keep in handy when trying to figure out the electron configuration of an atom. So I have more examples here, right? Let's look at argon, right? So argon has 18 electrons, right? So what would be the electron configuration? Wow, look how I spoiled you guys. The answer is right there. So let's check this out. These are the exponents I was talking about. 2, 2, 6, 2, 6. If you add that up, you're going to get 18 electrons, right? Right? And now if we look at this example here, we see that S holds 2, P holds 6, D holds 10. So this is one of those parts in biology and chemistry where it's something where you're going to have to memorize this concept. I highly recommend memorizing this chart, or at least memorizing how many electrons the S holds, the P orbital holds, and the D orbital holds. So again, with argon, we have 18 electrons, right? And if we see up here, we crossed out 1s, and S holds 2. We crossed out 2s, 2s holds 2. 2p, we crossed that out, 2p holds a maximum of 6. And then we crossed out, what else did we cross out? 3s, S holds a maximum of 2. Where are we at now? We have 2, 4, 6 and 4 is 10, 2, 12. So we're at 12 electrons. We still need 6 more electrons to fulfill that 18 electrons that's needed, right? So if we go back, boom. So we're going to keep going. So we have 1s2, 2s2, 2p6, 3s2, and now we're going to 3p, just 3p, 6, right? And now if we add it up, we get 2 plus 2 plus 6 plus 2 plus 6 gives us 18 electrons that we need, right? So yeah, that's pretty cool. I hope you guys are catching on to this. I highly recommend trying to get a good idea about that chart. If we even look at fluorine now, fluorine has 19 electrons, right? So we're going to look at our handy chart, 1s, 1s2, 2s2. We're at 4 electrons right now. So again, fluorine has 9 electrons. So how many electrons do we need left? 5 more. So now we're going to go to our 2p and cross that out. So 2p. Now remember, p holds a maximum of 6, but we don't need those full 6 electrons. We only need 5. So we can just put a 5 here, and that is the electron configuration of fluorine. And if you add that up, you get 2 plus 2 plus 5 equals 9. And that's the electrons that are in fluorine, right? All right. So if we go to our last one and do argon, oh, we did that one already. That one was up here, but this is a bit of more detailed kind of chart of the electron configuration. Okay, so let's go on to our last slide, and I will give you guys a moment to go ahead and do the electron configurations for these atoms here. You guys can pause the video. I was going to play the Jeopardy, but I figured you guys can pause it. So if we get into this, the first one we have is aluminum, right? So what we're going to do is go ahead and draw out our friendly chart, which I'll draw right here. 1s, 2s, 3s, and I want you guys to be like experts at this, like, you know, in your sleep, right? 2p, 3p, 4p, 5p, 6p, 7p. Then next would be 3d, 4d, 5d, 6d, and then 4f, 5f. All right. So aluminum, this bad guy has 13 electrons, right? So we need 13 electrons. We know that we can cross out this, right? So 1s, the maximum is 2 for s. So now we have 2 electrons. We can cross out 2s, and we know that s holds 2 electrons again. So now we're at 4 electrons, right? We still need 9 more. 2p, we can cross that out, and we know that it holds a maximum of 6. Where are we at now? We're at 10 electrons, right? So now we need 3 more. So we can cross out 3s, and then we have 3s, and how much do we need? 6, 8, 10, 3, but s only holds 2, so that would be 1s2, 2s2, 2p6, 3s2. So how much do we have so far? We have 2 plus 2 plus 6 plus 2, 8, 10, 12 equals 12. We need 1 more. So in this case, we would then go to 3p, and this is what our electron configuration will be. 1s2, 2s2, 2p6, 3s2, and then it would be, what did we have? 3p, and that's it. There would be like a 1 up here. That way now we have 2, 4, 10, 12, and 13. So this would be the electron configuration for aluminum. Pretty cool, right? You add up those exponents and it'll give you the amount of electrons that you are looking for. If you ask, you shall receive, right? So let's go to the next one, oxygen. A bit easier one, right? So if we go to our chart, let's see how I can do this. Ooh, you know what I'll do? I am just going to add the chart right here. And we're going to just use this portion as our reference, right? Instead of me just drawing it out every single time, which you guys should. So oxygen, We're going to start with crossing out 1s, 1s2, because s holds maximum 2. Cross out 2s, 2s2. We're at 4 electrons so far, right? We still need 4 more. Then 2p we can cross out. We know that p holds a maximum of how much? P holds a maximum of 6. But we don't need those all 6. We just need 4 more. So we can just say 2p. And that's it. 1s2, 2s2, 2p4. And that gives us our 8 electrons, right? 2 and 2 and 4 is 8 electrons. Pretty cool, guys, right? So now if we go to the last one, silicon, right? So I probably need some space for this one. It's going to be similar to aluminum, where we're going to have 1s2, and let me cross these out, where we'll have 1s2, 2s2, right? We cross out 1s, we cross out 2s. We're definitely going to use the 2p, 2p6. Definitely going to use the 3s, 3s2. So how much are we at? We're at 2, 4, 10, 12. We still need 2 more. So we're going to go to our final one, the 3p. 3p. So again, where are we at? 2, 4, 10, 12. We need 2 more. So this p orbital holds a maximum of 6, but we only need 2, just so we can make that 14. So then we have 2 plus 2 plus 6 plus 2 plus 2 equals 14 electrons. And we're in the money, guys. So that explains the energy levels of electrons and how to write out an electron configuration. And even with these photos, we still have the same concept. First shell holds 2, the second shell 1, 2, 3, 4, 5, 6, 7, 8 holds a maximum of 8. And the fourth shell, we only just have 4. All right, so that concludes this video. Let me know what you guys think. If you guys want more videos like this, definitely let me know. Like, comment, subscribe, do whatever you have to do. Watch the video over. There'll be more videos in the future. All right, so I'll catch you guys next time. Take it easy. Peace.